Hi everyone, I am Arnaud and work as a data scientist at Seldon, which is a company specialized in machine learning deployment. And with my colleagues, I also maintain the open source model explainability Python library Alibi, as well as Alibi Detect, which is a package that focuses on outlier, drift, and adversarial detection. And during the next 30 minutes, I will talk a little bit more about how you can use open source tools like this to monitor your ML models in production. The talk is structured as follows. I will first provide a brief overview of why you should care about monitoring in the first place, and then I will walk you through an excruciatingly long notebook to illustrate how we can do this in practice. So, as you probably know, the machine learning lifecycle extends well beyond the deployment stage. And a big challenge in MLOps is post-deployment monitoring to ensure you have a continued high-quality service provided by the ML model. But unlike traditional software monitoring, which involves logging metrics like request latency, frequency, or server loads, ML applications are actually more demanding. And we identify four additional areas following model deployment, which are key for the success of any ML application. So first, you would need to monitor your model performance, as well as metrics related to the incoming data. Then we can go on to detect drift, outliers, and adversarial instances. And finally, we want to be able to explain our model predictions as well. So for all of these areas, there are both algorithmic and infrastructure challenges. And in this talk, I will address both, so the algorithmic and infrastructure sides in the context of outlier, adversarial, and drift detection components. But before we dive into the different detection components, let's take a brief look at monitoring model performance and metrics related to the incoming data. So we differentiate between the two because the first requires obviously a ground truth, which comes with its own challenges. For performance metrics, the labels need to be fed into some system that calculates the metrics on the fly. And this can be done via an endpoint. So for instance, the open source ML deployment platform, Seldon Core, will expose a dedicated send feedback endpoint, which accepts labels and performs some user-defined metric calculations, which are often related to some business KPIs. We also need to decide on thresholds to take action, as well as which action needs to be taken. And this is actually harder than it sounds because the thresholds will depend on the use case, and in some cases may actually benefit from more sophisticated algorithms like change point detection. So the action to be taken then is also not obvious because it might range from doing nothing at all if the service is fine, to taking the model offline or trigger the model for retraining. But then another question arises, like which data would we be using for the retraining? And both types of metrics, so the performance and the incoming data metrics, are stateful and typically require selection of appropriate time periods as well. Finally, incoming data metrics range in sophistication from simple point-wise univariate estimates like mean and quantiles, etc., to multivariate or more sophisticated density estimates. And this brings us to outlier detection because at the core, it's basically a bit of a density estimation problem. So why bother doing outlier detection in the first place? Mainly because it's key for ML models because they often don't generalize well out of distribution. And on top of that, they can be overly confident on anomalous instances. So that can be because of a lack of calibration or, for instance, unreliable likelihood estimates. So as a result, we can't really trust model predictions on outliers, and we should be very careful in a production setting. But this is a very hard, unsolved problem on real data because there's no real silver bullet, and a suitable detector really depends on, for instance, the modality of the data, the dimensionality, etc. We also often don't really have access to a significant amount of labeled outliers, so they're often scarce, and that makes the problem semi-supervised at best. So while outlier detection is mainly about spotting changes in the input data, let's call it P of X, adversarial instances actually aren't that different in the input, so they're only marginally changed in the input space, but with a maximum effect, a maximum impact on the output of the model Py given X. Because at the core, adversarial instances are often instances which are very carefully crafted by applying some small perturbations to the original data with the goal to trick the machine learning model and change, for instance, the predicted class for a classifier. And this is illustrated by the simple image here, where the almost invisible perturbations flip the stop sign into a yield sign. And it's obviously crucial for safety critical ML systems like autonomous driving or healthcare applications to detect these kinds of adversarial instances and ideally correct them as well. And so far, we've looked at outliers and adversarial examples, but both are actually referring to individual instances. When we talk about data drift or shift detection, we actually look at whether two samples are drawn from the same underlying distribution or not via statistical hypothesis test. So now we're not looking at individual instances, but we're looking at distributions. And the goal of the drift detector is therefore to identify when the distribution of the requests for the deployed model, so the live requests, starts to diverge from the training data. And as a result, the model predictions might become unreliable. We will investigate two main types of drift. So we'll investigate covariate shift, which is drift in the input distribution, and shift of the predicted label or the prediction distribution. So both are types of unsupervised drift, since we assume we're in a setting where we don't have access to labels of the live data of the deployed of the model. And in practice, and especially on high-dimensional data like images, we will follow a two-step approach. So first, we apply a dimensionality reduction step, and then you can conduct your favorite two-sample test of choice, like the Kolmogorov-Smirnov with optional multivariate correction, or maximum mean discrepancy with a permutation test. And the example notebook will shed more light on the two-step approach. So that said, let's just move to the notebook. So I must admit, I actually cheated a little bit and already ran the notebook due to time constraints, and also maybe a little bit because I didn't want to break the notebook and start the recording all over again. So for the data set, we're looking at a very simple data set, which many of you will probably already be very familiar. And it's the CIFAR-10 data set. So it consists of 60,000 images, 32 by 32 RGB, which are equally distributed over 10 classes like airplanes, automobiles, birds, cats, etc. So here you can see a couple of the images. So let's go straight into our first kind of functionality, the first thing we want to test, outlier detection. In this case, we'll start off with a simple variation autoencoder, which is a fairly common type of outlier detector. And in a nutshell, when we look at vanilla autoencoders, they consist of an encoder and a decoder, and the encoder projects the input onto a latent space, which is typically of lower dimension than the input, while the decoder actually tries to reconstruct the input from the latent vector. And for a variational autoencoder or a VAE, this latent vector is not deterministic, but sampled from some learned posterior distribution with a mean mu and a standard deviation sigma, as shown in the image. So we sample from that, and then we try to reconstruct the original image. So for more information on VAEs, definitely check the fantastic blog post, which is linked in the notebook. And for outlier detection, what we will do is we'll train the detector on normal data so it can reconstruct the inliers very well. And then when the deployed model, the deployed detector, sees outliers, it will not be able to reconstruct it very well. So this leads to a higher reconstruction error. And if this error is above a certain defined threshold, the instance can be flagged as an anomaly. So first of all, we actually already pre-trained the detector on CIFAR-10, which is stored in a public Google Cloud bucket. So we'll just fetch it from there. But alternatively, here's the code to train it from scratch. So it's pretty simple. What you just need to do is define an encoder, a decoder, and a latent dimension, pass it to the outlier detection object, and then apply a very simple fit step. You can then save the detector like any detector in Alibi Detect with the simple save detector function. So let's see what actually comes out of the VAE, how it reconstructs a normal instance. In this case, the original instance is a boat. We reconstructed a boat. It's not the prettiest boat in the world, but it will do for our purpose. We also need to find a certain threshold to detect the outliers. And finding a good threshold is tricky and definitely not intuitive at all. That's why there is a simple infer threshold functionality to find hopefully a sensible value. So what you need to do is just specify roughly what fraction of the data set should be considered as normal or inliers via the threshold percentage. So in this case, like 99% of the data is considered to be in distribution, and then it will infer a threshold from there. To test the outliers, what we're actually going to do is we're going to create some artificial outliers by applying a random noise mask to the original instances. And in this case, you can see we're adding some noise to the board here, and we'll run the outlier detector on that. So we'll just call a simple predict step on the sample, which is both the noised, the perturbed instance, and the original one. And you can see on the original one, it did not detect, it was the reconstruction error was below the threshold, so it did not detect an outlier. And for the perturbed one, it did show, it did figure out this is clearly an outlier. And we can see as well, that's a nice thing about VAE, we can see per channel what basically the higher outlier scores, the higher reconstruction errors were. And it's pretty clear that some patches of the noise mask are flagged as outlier areas. So now it's clear how the outlier detector works. We can actually deploy it. And for deployment here, we'll use Seldon Core, which is, as mentioned earlier, an open source deployment platform on Kubernetes. And we also use the eventing-based project Knative, which connects serverless components with event streams. And this will be clear from the diagram. So as you can see in the diagram, on the left, we have the Seldon Core deployment with a payload logger, which sends events containing model requests and response payloads to the Knative broker. And the broker can then farm these out via programmable triggers. And these can be farmed out to different serverless components like the outlier, adversarial, or drift detection modules. And it does so asynchronously. Then the events produced by these components can be sent further, for instance, to alerting or storage modules. So this clean separation of concerns between the model and the monitoring components actually allows them to be scaled separately as needed. And Knative makes it then possible to scale the services down to 0 if no requests come in, and scale up as the demand increases. My colleague was already kind enough to configure a cluster on DigitalOcean with Seldon Core installed, but the necessary configuration steps to set everything up from scratch can be found in the linked notebook. Okay, let's walk through it. So first, we need to get the IP address of the ingress gateway for our cluster to direct the requests to, and we also get the host name of the outlier service as well. Then we define some simple utility functions for the prediction of the deployed model and the outlier detector. So let's just run those on an actual instance. So you can see we'll make a prediction on the original instance. The classifier, the resonant classifier, correctly says, okay, it's a ship. And then what we can see is we will check the message dumper for the deployment for the output of the outlier detector. And the message dumper will contain the information of the outlier detector, such as like the feature-wise scores and whether it's an outlier or not. And it again says, okay, it's not an outlier. We then do the same on the perturbed instance. We show it here quickly, make a prediction. Although it's still a ship, the outlier detector, as we can see from the message dumper, correctly figures out it's an outlier, and again highlights the same feature, kind of the pixels where why it thinks it's an outlier. So it highlights the mask, the noise mask. So okay, more or less mission accomplished, and we can move on from outlier detection to adversarial detection. For adversarial detection, we'll follow the methodology in a paper called Adversarial Detection and Correction by Matching Prediction Distributions. And the method is pretty simple, pretty straightforward. I'll try to give a clear overview in very briefly. So as mentioned earlier, adversarial examples are almost indistinguishable from the original instance, but they fool the classifier and change the model prediction. And since the impact is mainly felt in the model output space, this is where the detector will focus on. Because there's almost no change in the input of the adversarial instance compared to the original one, but there's a big change in the output, so in the prediction. So the idea for the adversarial detector is as follows. First, we train an autoencoder, but not with as goal to reconstruct the original input X, but instead we want to make sure that the classification model predictions on the output of the autoencoder, X prime, are the same as on the original instance X. So we don't incentivize X prime to look like X at all. And as a result, the carefully crafted perturbations around X, which fool the classifier, they actually do not transfer to X prime. We can then simply compute an adversarial score, which we measure as the KL divergence between the classifier prediction on the original instance X and X prime. And if the score is above a threshold, again, the instance will be labeled as an adversarial instance. And if the instance is adversarial, we can actually use the prediction of the classifier on X prime instead of X for kind of downstream purposes. And this procedure is shown in the diagram. More detail can be found in the text blob here in the notebook and in the paper which is linked. Okay, so then because we're using a slightly different model, we're going to add some utility functions to simply rescale the data. We'll load a pre-trained classifier as well, and just make sure that that our ResNet classifier is correct, and we just check the double check the accuracy. So it's about 93% on the test set of CFAR10, which is decent enough. And we'll apply two types of adversarial attacks on the data sets. The first one is a Carlini and Wagner, and the other one is a slide attack. And they're pretty powerful, as you can see, because the accuracy of the machine learning model of the ResNet classifier basically goes from 93 to 0%. And we can also see some of the images of the original compared to the adversarial images. So the original here is a plane. The model, the ResNet classifier correctly identified it as a plane. And the adversarial image is basically looks the same, but it's classified as a ship. Same for the frog, which is turned into a bird. So this is clearly an issue that we want to rectify. Same as for the outlier detector, we can fetch a detector from the Google Cloud bucket. But again, you can just train one from scratch yourself. It's pretty straightforward. Same thing as for the outlier detector. We just define an encoder and decoder and pass that with the classification model to the adversarial detection object. Then we call the fit method on the adversarial detector and can save it in exactly the same way as the outlier detector. Okay, so let's see what actually the impact is. So as you saw before, the accuracy after the attack was reduced to almost zero. But then when we look at the accuracy on the reconstructed instances by the adversarial autoencoder, the accuracy is brought back up to well over 80%. So that's pretty good. That's not bad at all. And let's investigate like what it looks like and why what is going on really. So we see again the original CFAR10 image, which is correctly classified as an airplane with an adversarial score here of almost zero. But then when we look at the adversarial image, which looks almost identical to the original, but classifies the image as a dog, the adversarial score has spiked up to over 5. And interestingly enough, in the last column here, you can see the reconstruction of the instance by the adversarial autoencoder. So as you can see, it's clearly not incentivized to reconstruct the input, but it just cares about the decision boundaries. It just cares about making the same correct model prediction as the original instance. And the small perturbation which is applied in the adversarial instance does not transfer to this kind of noisy looking image. And the noisy looking image actually produces the right class. You can see the same thing for other instances, like the horse, which is fooled into a truck, but actually the reconstruction by the adversarial autoencoder corrects it back to a horse. And this is the same for the slide attacks. We can plot this for all the instances and see that then construct the receiver operator curve. And we can actually see that for both the attack methods, the Carlini-Wagner and the slide attack methods, it's the detection is doing a very good job. So the AUC is close to or above 0.9, which is not bad at all, given that our accuracy went all the way back down to 0. And same for the other, as for the outlier detector, we can just infer thresholds that we will use further down the line. So what I want to show now is how the diagram is really executed in a very simple way by the adversarial detector. So what I'll do here is just sample some new data sets where 25% of the instances come from the Carlini-Wagner attack, and the rest from the original CIFAR-10 test set. So if you look at the accuracy on this new data sets, it's not great. It's because of the attacks that the adversarial instances that I introduced. It's all the way down to less than 74%. What I will do now is basically run the correction functionality from the adversarial detector on the same data set. So what this basically does is just execute the diagram that we saw here. So it will reconstruct the original input. It will calculate the adversarial score. Then we'll check, is the adversarial score above a threshold? So is it an adversarial instance or not? If it's below the threshold, we just use the model prediction on the original instance. If it's above the threshold, we'll use the prediction on the reconstructed instance by the adversarial autoencoder. And by doing so, which is called the correct method, we actually bring the accuracy not all the way back up, but we bring it back up to 82%. So that's all like a good 8% improvement over the uncorrected method. So that's pretty good. And we can actually further boost the performance quite a bit by adding some other tricks which are highlighted in the paper, like temperature scaling on the output and including the KL divergence of not just the output, but also of the hidden layers of the model. So all these functionalities are implemented in Alibi Detect. So you can just play around with it there. So for the final part of the talk, we actually moved to drift detection. And as mentioned before, the drift detector applies feature-wise to sample Kolmogorov-Smirnov tests, followed by a multivariate correction of the obtained p-values for each feature. Because for high-dimensional data like images, we first want to reduce the dimensionality before computing the KS statistics. Imagine for a high-dimensional image, you need to, for each pixel, basically start doing a KS test and then aggregate those. That's not really very useful. So we need to add a pre-processing step to reduce the dimensionality, and then we can detect drift on the pre-processed data. And there's two methods we will follow. We will basically follow suggestions made in the paper called Falling Loudly, an empirical study of methods for detecting dataset shift. And the first one is basically to use an untrained autoencoder, so just a randomly initialized autoencoder, which predicts the input on a lower latent dimension. And this allows to measure covariate shift. The second method actually uses the softmax output of the classifier and enables us to detect drift in the distribution of the model predictions. We use the same data set, CIFAR-10, but to test the drift detector on, we'll also use CIFAR-10C. So CIFAR-10C is actually contains the same images as CIFAR-10, but corrupted by different types of noise, blur, brightness, etc., at different severity levels. So the more severe the corruption, the bigger the impact on your classifier performance. We then randomly sample a reference data set from CIFAR-10 against which we will test or drift, as well as the data sets coming from the same CIFAR10 test sets, and which should not reject the null hypothesis since it comes from the same data. And then we'll also sample some data from 4 different types of perturbations. You can see them here. We use Gaussian noise, motion blur, brightness, and pixelation. So as an instance here, you can see the original image, Gaussian noise applied to it, motion blur, etc., etc. And you can see that they really impact the accuracy of the original classifier a lot. So the original classifier is around 93% accurate, but this is brought all the way down to 22% for Gaussian noise. So given a drop in performance, we really, really want to detect this harmful drift. Okay, let's do it then. So first, we'll use the first pre-processing method, the UAE, the untrained, the randomly initialized autoencoder. It's pretty simple, so kind of getting used to defining an encoder now. And the encoder we just pass to the KS drift detector as pre-processed quarks, together with the reference data sets and a desired level of p-value for the test. And because we don't need to fit any data, we can just predict straight away. Let's first check whether the detector flags drift on the data set, which comes from that same test set distribution as on CIFAR10 as the reference set, and it doesn't, so that's good. We can also see for the p-values of the individual features that they're well above 0.05, so they're kind of from the same distribution. When we do the same thing on the different corrupted data sets, for each single one of them, it's a clear yes, it's clearly drifting, so that's good. We do the same thing for the other pre-processing method, so which we call BBSDS, which comes from another paper called Detecting and Correcting for Label Shift with Black Box Predictors. So here we use the softmax layer from the classifier to detect the drift, but we can actually use other hidden layers as well, just by specifying the layer index which we want to extract. And again, we just pass it as pre-processing quarks to the drift detector and run the exact same prediction method. Same as for the other pre-processing methods, it doesn't drift on the data coming from the same distribution, but it does on the perturbed instances. So it's all very, very fun and exciting to detect drift on monitoring via covariate and label shift. But at the end of the day, what we really want to measure and care about is whether the model performance has been impacted. Like, is there model deterioration going on, and can we flag that? And the great thing is we can actually leverage the adversarial detector for this. So instead of using a pre-processing step like the encoder, we can just pass the adversarial scoring function. So the exact same adversarial detector, we just pass the scoring function, which spits out one number, so it's a univariate KS test, and we measure drift on that. And interestingly enough, that works very well. So again, on the original kind of test set distribution, it doesn't flag drift. On the others, it does. And what is actually more interesting is when we look at this plot here, what this plot shows, on the left y-axis, it shows the adversarial score, and on the right axis, the classifier accuracy. Then the x-axis displays basically increasing corruption severity levels applied to the CIFAR10 datasets. And the orange bars at each level show the scores for the instances where the model predicted the correct class for both the original and the perturbed instance. And the green class shows, on the other hand, the scores where the model was initially correct, but because of the corruption, the model flipped to an incorrect or wrong prediction. So this is what we call harmful drift. And it's clear that at all severity levels, the drift score for the non-harmful instances are actually very similar to that of the original CIFAR10 test set. But for the harmful instances, it's way higher. So it will be flagged up and picked up as drift. So that's really, really good. And in the same way as the outlier detector, with using the same cluster, we can also just inspect the drift component. So in this case, we'll just accumulate batches of 5,000 instances in the drift detector before we actually make the drift prediction. So this can be specified in the deployment YAML, and it's very flexible. So you can see here, we basically accumulate in batches of hundreds, and the drift detector will only make a prediction once the batch is full. So once we reach 5,000 instances, and then drift will be flagged or not. So we do this on the original data set, and again, there's no drift. And when we do this on the corrupted data set with Gaussian noise, we do pick up drift. So the deployed model does its job. So great, thanks a lot. And this brings us to the end of the talk. And in a nutshell, to conclude, I can't stress enough how important it is to monitor your machine learning models and incoming data distributions if you want to stay on top of how your model is doing in the wild. And while there is no real silver bullet for any of the outlier, adversarial, or drift detection tasks, there are tools available like Alibi Detect, Seldon Core, and Knative, which are flexible enough to tailor the detectors to your needs and also deploy them in production. So for those who made it all the way to the end, thanks a lot for listening, and I'm looking forward to answering all of your questions during the Q&A. The notebook with all the examples will also be made available on the Alibi Detect GitHub repo.